And now I'm very pleased and honored to present our esteemed keynote speaker for today. This is Dr. Chih-Yuan Lu, who is the president of Micronix International and the chairman and CEO of Ardentec Corporation. He earned his PhD in physics from Columbia University. He is the founder of multiple companies and was a project leader at Bell Labs. He is a fellow of IEEE, a fellow of the American Physical Society, a recipient of the IEEE Third Millennium Medal, an honorary chair professor of National Taiwan University, and has many other awards. He's written more than 300 technical papers, has more than 140 patents, has written articles in newspapers and magazines about education, science, technology, and public service, and has contributed to 2 books. Today, he's discussing future prospects of semiconductor memories, advancements, and challenges. Welcome, Dr. Lu.
Thank you, Jennifer. Thank you for your introduction. Good morning and good noon for people in the United States, and good evening for people from Asia and Europe. My name is Chih-Yuan Lu from Micronix International and Ardentec Corporation. Today is my great pleasure to be invited by ITC to present our view on future prospects of semiconductor memories. Although we cannot get together in a conference room, but I trust this kind of a virtual conference will reach even much more people around the world to join this truly international flagship conference in test area. Okay, let's go. As you can see from these photos, that's an interesting contract. From 1956, an IBM Model 350 disk storage unit. It's only 5 million 6-bit character at that time, 6-bit. That's only 3.75 megabyte, but it weighed more than 1 ton. And cost you a lot, $750 per month to lease this kind of device with you. But if you see on the right-hand side, this is the recent 15 years, from 2005 to last year, 2020. And you can see this micro SD card is as small as your nail. It's just a jump from 128 megabyte to 128 gigabyte. And today is 1 terabyte. It's take only 215 milligram and take about $200. So memory technology really advanced exponentially. We believe semiconductor memory has a very bright future. It's a big data era coming, and that needs a huge memory device. In many applications, such as AI applications, edge intelligence, 5G, automobile application, all need large amount of memories. Actually, the COVID-19 pandemic challenge recently just accelerated the momentum toward digital life. Our lifestyle really changed a lot. And this is augmented with a lot of smart devices. And there is also further diversification in memory devices, also in many applications that need more optimized performance, thus resulting in many product specs. So recently, the whole semiconductor enjoy a fast expanding market. In particular, we believe the role of memory is gradually changing from a passive memory or storage device to become a central role in computing system. This will be into a memory-centric era. I take this as example. Let's look at an automotive memory. I believe that's the next application killer. Almost all nations in the world will encourage electrical car to replace the traditional gasoline car. In addition, self-driving car will also trigger even much more automotive electronics. It is forecast that the self-driving car will generate 4 terabyte data daily. So those data need a place to go and to be stored and to be used. And also, it requires huge memory bit in DRAM and flash memory devices. They need to be ensured automobile grade. And that really need both technology and the testing effort to ensure this best memory reliability quality. And for ADAS, that's advanced driver assistance system, that to work with intelligent device near a sensor and a camera for edge computing that need a new memory architecture design, and I will introduce to you for next moment. I here give you some example. That's you can see. The world is really hungry for memory and the bandwidth. Memory for density, also for the speed for the density in big data era. This is a very interesting recent example. You see this is one chip. This chip size is just like a dinner plate size, a dish. You see the fork, the knife here, it is so big. This chip is occupy a whole 12-inch wafers. It's consistent of 40 gigabyte SRAM, 20 petabyte per second bandwidth, and without DRAM. So save a lot of DRAM I/O power. So this is a crazy, seems a crazy devices, but it's really interesting and just like a very good example talking about the problem right now is from the memory to the system. And also you can see this is high bandwidth memory DRAM. You see this high density memory DRAM stacks dies DRAMs through silicon via. This provides several terabyte per second bandwidth. And this is much faster than DDR5. Okay. And then another is interesting thing is this crazy mining machine for those Bitcoin. They are very hungry with memory too. They take a lot of terabyte solid state disk. They really actually put a lot of metadata into there and use there frequently as a semi-DRAM. And they even destroy a lot of due to the endurance. All these examples, interesting examples, are illustrating the need of high density and high bandwidth memory. And here I give you a very quick about the major semiconductor memory market. SRAM, actually, it is almost all embedded in CMOS devices. It's a huge business, but there are very seldom standalone SRAM right now. DRAM, very fast DRAM, still this working memory, its market size is about $70 billion and fast growing. NAND flash with huge of bit produced, but market size is about 50 billion and fast growth. And NOR flash is also grow fast. And you can also see there are a lot of emerging memory. And frankly speaking, this emerging memory still in the emerging stage. Their market size is still not so big, but full of their potential. You can also see there is a performance gap between DRAM and the NAND flash. The performance gap is about a factor of 1,000. So people are talking about a lot of intermediate buffer memory, such people-called storage class memory, and persistent memory, DRAM-like, of these things. This is also a very potential area, but it is not clear how it will go. In this talk, due to our limited time, I just will focus on non-volatile memory as an example. This slide shows you an overall of the most popular non-volatile memory landscape. Flash memory remain as the dominant non-volatile memory. 3D NAND technology and the manufacture are proven and occupy almost all of the market share. 3D stacking is already a mainstream technology. In addition, some company like Micronix is now developing 3D NOR flash. It is to continue the NOR flash slide scaling and provide a more advanced application. There are many other emerging memory, as I said before, like a phase change memory with 3D cross point. There are magnetic RAM, there are resistor RAM, and the ferroelectrical RAM. And those memory race are still continue. Universal memory is not emerging yet. Various emerging memory have their own advantage in respective niche applications. However, there is still a long way to go to become a mainstream memory product. Now, let's focus on the recent development of the mainstream non-volatile memory. Let's from 2D to 3D was the major breakthrough revolution as the planar scaling end up its limitation. The end up such as the coupling. When you scaling down, the coupling is too much. When you change to the 3D, the coupling dramatically reduced. And also, when you scaling down the gate, there are few electrons, too few, into the storage gate. Therefore, go to the third dimension is a very nature and effective way. In 3D non-volatile memory, physical dimension of a single unit is no longer scaled drastically. However, due to the third dimension, stacking, make the equivalent design rule of the storage cell keep on scaling as the economic Moore's law demand. I believe there are another 15 years life extension for this quasi-Moore's law in memory can be expected. However, the conventional 3D pile-up stacking process will not work for bit cost scaling. Let's take the photo mask as an illustration. Let's see on the left-hand side. If you build one layer, you take a DRAM, take a 27 mask. You extra added a layer, take your 5 another mask. So if take 96 layers, the total mask will be about 500. But there are some very innovative device and processor approach on the right-hand side was invented in 2007. As you see here, we just put all the layers and just use one edge. So the mask layer only added a very few, as you can see here. If you use this approach, the cost will not decrease, but eventually increase dramatically. But use this approach, the cost of the bit decreased substantially, just as Moore's law required. As you can see here, I just show you by this cartoon. This is the typical NAND cell string in 2 dimensions. Actually, you put this and in 3 dimensions. So the area, in planar area, is shrink from this area into such a small area. This is another thing to illustration for your have more vivid, visible to see. This is 2 dimension. It's a turn it, stand up, and then you put more and more. This is a 3 dimension one. As you can see, this is a final structure. This is a 3D NAND. This process is a really innovative, but also very challenging. You see, every single cell become a gate all around memory cell. So it's a very robust, and all the scaling side effect almost disappeared with this kind of structure of cell. Okay, now let's review the status of a 3D NAND flash currently. Now it's the best high density and low cost data storage device. The 3D NAND scaling right now is already close to 200 layers, and also for TLC and QLC. That means a 3 level of 3 bit in a physical cell, the 3 level cell or 4 level cells. That's already been achieved and manufactured in 2020. And 1 terabit single cell, single chip is already being produced. The solid state disk bit cost is as low as 1 gigabyte, only take 10 cents. However, for the NAND, the trouble is the slow latency. The latency take about 100 microseconds. That's a chip plus the controller. And a very large page size is about 16 kilobyte. And also limit endurance. For single level, 1 bit per cell, that's about 50,000 times the endurance can be guaranteed. But for 3 bit for cell, it's only 3,000. But for 4 bit for cell, only 500. So there are trade-off of the cost of the bit and some of the performance and their quality of endurance. Also, 3D NAND, and actually even for the 2D NAND, is not a perfect memory. NOR flash is a perfect memory, but the NAND is not a perfect memory. So need a very complex controller to fix a lot of things, make it usable. So a lot of algorithms need to put into the controller to help this NAND flash, such as error correction code, garbage collector, reader re-entry, and wear leveling, and refresh. A lot of skill that need to be put there, make this device usable, working. But also some people is doing very fast single level cell 3D NAND for very fast solid state disk that can be compete with the so-called 3D crosspoint, and that the speed is as high as 10 microseconds. And in order to make this chip, it's more and more density. The peripheral also become very big because there are the bandwidth and the number of area you need to divide it. So the CMOS people is achieved to put the CMOS under the array. So that's called CMOS under array. This will make the process even more difficult because when you put a CMOS there, when you build this 200 layers of array on top of it, there's a lot of thermal process will affect each other. And also the process variation cause a lot of window variation and operation variation. So that also need to be overcome. And we see the future prospect of SAND flash. More and more high stacking is doing. And we can see about 400 layers is possible. So this is amazing. And using what? Using multi-deck. Because for each edge, for 400 layers is really difficult for present process equipment. But 200 may be okay. So you do it twice. Do it 200 times and then stop. And do another 200 times and connect into here. We also try to build very high bandwidth. This using NVMe the standard, interface standard, can do that. And that need a lot of ECC, advanced ECC, such as low density parity code, polar code, and the machine learning code. This is all in development, and we think there is a lot of potential of this advanced ECC. And also there are also many innovative structure, like double density cell, cut the hole into half, so that become two physically one, separate, such increased density by double. And also confine the silicon nitride from cell from the other, such that we can also shrink the cell's dimension. And also people use 3D IC skill, such as copper bonding, to connect 3D and the CMOS for a lot of variety. In addition to the NAND flash, let's look at the NOR flash. NOR flash still the most simple, useful, and reliable longevity flash product, especially for this longevity, for automobile, for the very reliable. This is very important. It's a very fast random access. That is NAND flash cannot achieve. It's about 100 nanosecond random access, much faster power on than NAND flash. And easy to use, no need a controller, just a single chip solution. Very cheap, affordable. And then the price for 1 gigabit single die is really a good solution to the system. Automotive grade reliability and friendly as a longevity for many computing application. Right now, such as a lot of AI, IoT, they need only small size of memory. So make this NOR flash fast growing. However, the problem is 2D NOR flash cannot scaling anymore when less than 45 nanometer. This is not due to the construction. This is due to the electricity effect. When they smaller than 45 nanometer, a lot of side effect become, all this advantage become disadvantage. So we're talking about doing this maybe into more innovative, such as we can do that with a vertical 2T, two transistor NOR flash with a low power. And we can also doing 3D stacking, as you see here, 3D stacking. We can also put a micro heater into this structure, such that making the endurance can be as big, as long as the 100 million times endurance. You make it self-healing. And also this computing in memory and in-memory search function make this NOR flash a lot of innovation application in the future. This is another thing I show you here. Like in a flash memory, any memory right now, is added a lot of function, such as security. This is as a common flash memory. As you can see, the data has come here along the way to the host. People can cut in here. So we need to make a security engine. Coupled with this, when you send the data out to the host, it is encrypted, it is authentication, and you can be much more secure. However, people still can cut in here. So make it embedded into a monolithic solution is further providing the good solution. You have provided all these kind of function. Here I will just also talking about a little bit about the 3D scaling challenge. As you can see, we need to still scaling as a Moore's law, cost-wise. So from 24 levels, when you will reduce your cost by a half, you need to do 48. When 32, you need to reduce your cost by half, you need to do 46, and double. However, when you double your layers, your array height will be double. That's too much. That's put too many heavy burden to the process engineer. So when you increase by double over the layers, the array height, we try to make it just a little bit increase, not increase that much as a doubling. But still, this height is increased. So we talk about the present manufacturers around here, the most advanced one. The aspect ratio, we needed to have a high aspect ratio process, and then a poly uniformity to do that, and the wafer of warpage, and the metrology to measure it, and also make the current, driving current, very difficult. But we still try a lot to make this increase as least as possible. In order to do this, each individual layers, we need to thin down it. That causes another challenge, like reliability, the resistance, such as RC delay, and also a lot of process difficulty. I just quickly give you the C as an example. As you see, high aspect ratio. You need to etch so high aspect ratio, so you need to use the deck stacking. Okay, as you see, the top and the bottom have a variation, and the edge, the uniformity also change. And also because the bit line is so long, such that the driving capability is an issue. And also you see, when you do this, the wafer become a potato shape. When you do the atomic layer deposition, the wafer warp as this, and you use the CVD, the wafer warp as another way. And you need to metrology to monitor, to watch how to do it, how to improve your process. And in order to reduce every individual oxide nitride pair, thin down. This is thin down. Make it this thinner and thinner, such that you have a double, the layer is not so. However, when you do this, the transistor is closing. So the transistor will cause a lot of electrical side effect. The electron and the hole will recombine, drift, and the thin down that cause a lot of stress, reduce the bending. And also here, you can see when you do this process, when you need to fill in these gaps, it's very difficult. Okay, let's quickly jump into another area. Talking about the future memory. The memory will different from the previous history memory. All the time, flash memory go to DRAM as a shadow of DRAM and go to the process. New paradigm is coming because of high bandwidth and added some computing function into the flash. And then the flash memory will closer to the processor, such that the new innovation flash memory will expect the memory get closer to computing and become a computing part of the devices. As you can see, this is one example I give to you as I say, computing in memory. For example, due to very high density, the NAND flash, 3D NAND flash, very nature is word line. It's word line is as an input. As their memory cells conductance can serve as a weight. For the AI, such a deep neural network actually is doing this math, multiplication and accumulation, calculation. This is a very nature happening this, okay? So there are ways to use flash memory and other emerging memory to perform an analog MAC, this is so-called MAC operation, such that this can be a very nature to be in a perceptron of DNN computing. The computing in memory is a very hot topic recently, a very potential, and I expect it's a potential paradigm shift for memory. Flash memory had advantage because of a high density of a very mature commercial product. So this is a very stable and high on-off ratios such that we can make the window very big. And also we can use this as an in-memory searching effect. It is possible to design an in-memory search such as a non-volatile TCAM. TCAM is the iterator and accelerable memory with flash memory. It's a complementary to edge computing architecture. We also expect this is a very good tool for the AI. Another thing very important I take here, memory reliability is a major priority. Okay, actually, especially the mainstream NAND flash is an imperfect memory. It needs to be protected by a lot of ECC code. As you can see, DRAM, SRAM, or NOR flash cannot use ECC freely because of the speed requirement. However, the NAND flash also can using a lot of ECC by controller to reduce the cost a lot and make virtually the yield almost like 100%. However, to doing all these things, chip testing complexity become a lot. As you can see, for the advanced memory, the testing item parameters we need to adjust. Right now it's almost already more than 1,000 parameters we need to adjust to make the device work. And then the testing time is increased dramatically, as you can see here. From 2D to 3D, from low density to high density. That's a really significant change, the testing time. So due to that, in our critical aspect of product development, we need to do technology development, chip design, and product testing, and reliability quality. This is what we want to deliver. So this testing here, you guys in this society, you can contribute a lot, especially to adjust, as I will show you. As an intelligent parameter tuning in wafer sort testing, we need to inter-chip a lot of variation. Actually, this is a variation from by die variation. And we need, you doing the wafer sort stage, you can adjust, you can give a lot of functional parameters to support that, to deliver working function chip. Such as that we're talking about co-optimization of controller with the testing is very important. As you see in a variation of a layer A and a layer B, there are process variations such that the layers that we to read is shifting. But however, with controller, with some AI learning here, we can adjust this, make this kind of a chip still a good chip. So we expect a good opportunity to implement machine learning in intelligent controller to optimize operation conditions, such as read level. So I encourage this society, testing society, to consider intelligent test and the control scheme to co-optimize the device technology and the circuit design. That will be greatly improve the memory quality and the testing efficiency. So I will summarize my talk. We see semiconductor memory device will be embrace a bright future. We believe in the NAND flash, NOR flash, and DRAM market will continue to fast growing with the new innovative technology advancement. New emerging memory architecture and the device may arise to complement the conventional computing for memory-centric computing era. Much more complex memory chips thus need tuning parameters and the testing effort in advanced memory device. We encourage innovative, intelligent memory testing to co-optimize with the process technology and the product design to support advanced memory product. Thank you for your attention. Thank you.
Thank you very much, Dr. Lu, for a wonderful talk. There's just one question. So when you were referring to the fact that you have computation in memory, and in addition the reliability and the fact that you need to find errors in real time, how do those two things intersect?
Okay. Due to the process becomes so complex, okay, process variation and all those things is cannot avoid. We have to live with those complex process variation. So in test, especially like in a wafer sort, a lot of parameter programming can be put into that. So make each chip is individually programmed such that the variation can be eliminated, such that also improve the quality largely. Without this kind of capability and advancement, the reliability is almost impossible to achieve, especially for the automotive requirement, like not PPM. We are talking about the PPB right now.
Thank you very much, Dr. Lu, for both answering the question and for the wonderful keynote address. We really appreciate it.
Thank you. Thank you.